This is question 1 from book 1 based on the 2020 NEC by electricaltime.com. A machine that operates at 120 volts single phase with a maximum current of 30 amps is 300 feet away from its power source. What would be the minimum size conductors to limit the voltage drop to 2.5%? Just want to take 30 seconds to let you know what we do here at electricaltime.com. We do online electrical classes from the comfort of your home. And then we also have this free service. So if you click on the subscribe for free NEC questions, Monday through Friday, you'll get an NEC code question and an answer sent to your email. All right, so back to our video. And the answer to this question is going to be 1AWG. All right, so now let's go take a look and see how we got to this answer in our video. First thing that we have to do is identify some of the things in the question. So we see we've got 120 volts. We have single phase. We're also being told that we've got 30 amps. And that this is 300 feet away from its power source. And we're told to limit the voltage drop to 2.5%. All right, so let's go see how we solve this problem. All right, so step 1, let's look at the standard voltage drop formula for single phase. And that's this over here. And it says VD is equal to 2 times K times I times D divided by CM, where VD is equal to voltage drop 2, and this is for single phase, very important, or 1.732, and that would be for 3 phase. We've got K, and that's going to be 12.9 ohms for copper, or 21.2 ohms for aluminum. Then we have I for amps. Then we've got D for distance one way. Again, that's one way. Then we've got CM, and that stands for circular mills from chapter 9, table 8. All right, and we're going to be looking at this table a little bit later in our video course. But let's do this. We're being asked to find, what size conductor. And let's go take a look at the question again. And I'll repeat it. A machine that operates at 120 volts, a single phase, with a maximum current of 30 amps is 300 feet away from its power source. What would be the minimum size conductors to limit the voltage drop to 2.5%? So we're being asked, what size conductor do we need so that we're limiting the voltage drop to 2.5%, and that would be 2.5% of 120 volts. So what we have to do with this voltage drop formula, we have to rewrite it so that we're solving for circular mills. And let's do that. And that's going to be found in step number 2. But what I'm going to do here is I'm just going to highlight the things that changed from the first version of the formula to the second version of the formula. So, all right, so let's take a look at our original formula where we've got VD, voltage drop, is equal to 2 times K times I times D divided by CM. Now, when we're solving for CM, we're going to take CM and we're going to put that in the front of the formula like this. So CM is going to equal 2 times K times I times D, and then we're going to take the voltage drop, VD, and put that at the back. All right, so an easy way to remember the voltage drop formula, and again, I'm going to erase everything up here. Watch this. Voltage drop is equal to 2 kids divided by CM, okay? Voltage drop is equal to 2 kids divided by CM. If you can remember that and you're looking at a test question like this, just remember voltage drop is equal to 2 kids divided by CM. Now when we're solving for CM, we're going to be rewriting that formula just like we did over here. And let's do it again. So CM, which stands for circular mills, is equal to 2 kids divided by VD. And circular mills, CM, is equal to 2 because that's single phase. 12.9 ohms, and that's going to be for copper. So in the question, if we don't specify if it's copper or aluminum, it's going to be copper. Then we've got 30 amps, and that was from the variable I. And then we've got 300 feet, and that's from our variable for distance. Then we divide that by 2.5% of 120 volts. And we got that 2.5% from the question where we're saying, to limit the voltage drop down to 2.5%. And 2.5% of what? That's going to be 2.5% of 120 volts. So when we do all this math, CM is now equal to 232,200 divided by 3. And CM is going to equal 77,400. And that's 77,400 circular mills. All right, so now in step number 3, we are now going to go to chapter 9, table 8, and find the minimum conductor that is at least 77,400 circular mills. Let's take a look at the third column, which is titled circular mills, and find the closest circular mills that is at least equal or just greater than or calculated circular mills of 77,400, and we find 83,690 circular mills, which is equal to 1 AWG, which is the minimum correct answer. We could use a conductor larger than 1 AWG. However, the question asked for the minimum conductor that would limit the voltage drop to 2.5%. And at this point, you should have put the video on pause so you can go take a look at chapter 9, table 8. And if you don't have your code book, just go back to our website, electricaltime.com, and just go buy your code book. All right, and that's our website there, electricaltime.com. Now, the NFPA has a really nice tool, and that is called the NFPA link, and that's where you can get the code book on your cell phone, or if you have a tablet that has internet access, or on your computer. And I'll write that down over here. And again, it's a fantastic tool. NFPA.org is the website. And again, you're going to be looking for something called NFPA link. I highly recommend it. All right. So back in our question, we identified the minimum circular mills, and that was 77,400. So what we're going to look here is at the area, and we're going to look here at circular mills. And again, we're looking for 77,400. So when I look down here, I can see that 2 gauge over here is equal to 66,360 circular mills. And that is too small. So now what we have to do is to look at the next size, and that's going to be 1 AWG, and that's equal to 83,690 circular mills. Again, when we did our formula, we were looking for 77,400 circular mills. And the 2 gauge was too small, so it can't be too small. So then we go to the next size up, and we see the 1 gauge is 83,690. Now, could we go to a 1/0? Sure, but the question wasn't asking for that. It was asking what's the minimum size conductor to limit the voltage drop to 2.5% of 120 volts. All right, so we all got the answer here. And that was answer was D, 1AWG. Use the voltage drop formula and solve for circular mills. All right, so I got a bonus here that's not in our textbook, and that's just for the people here watching, the video here on our members-only video club. All right, so here goes. Now that we just calculated the required conductor size so that we limit the voltage drop to no more than 2.5%, let's now calculate the exact voltage drop of these conductors in EMT using our good old friend called Ohm's law. So step one, let's write what we know so far. So we know we've got 120 volts. We know that this is single phase. We know that we've got 30 amps. We now know the conductor size, and that's 1 AWG conductor, and obviously that's going to be copper. And we also know that the maximum voltage drop, is 2.5% of 120 volts, which is equal to 3 volts. So let's go to step number 2. And let's find the AC resistance for 1 AWG conductor in EMT for 1,000 feet of conductor. And here we're going to go to Chapter 9, Table 9, and that is called AC resistance and reactance for 600 volt cables. And here we're going to find the 1 AWG conductor in the first column. And again, we'll take a look at the table in a little bit, but let's just walk through these steps together. Then we're going to find the resistance reactance for steel conduit in the sixth column for uncoated copper, which is 0.16 ohms for 1,000 feet of conductor. Again, that's going to be 0.16 ohms for 1,000 feet of conductor. That's very important. All right, so step 3. And you know what? Before we even do that, let's go take a look at Chapter 9, Table 9. All right, so here is Chapter 9, Table 9. And what we have to be really careful of in this table, we have to make sure we're looking at the right row. And what do I mean by that? So up here, we see where it says ohms to neutral per kilometer. And I'll zoom in on that. And then we've got over here, ohms to neutral per 1,000 feet. Got to be real careful when you're looking at this table because you can easily make a mistake. So let's just sort of look at this here, and let's look at, the first set of numbers here, which is going to be for 14 gauge. So let's say we're looking for the alternating current resistance for uncoated copper wires. And we can see for steel conduit that we got two sets of numbers. So we've got 10.2 and then we've got 3.1. So if we're looking at the ohms to neutral for 1,000 feet, that's going to be 3.1. If you're looking for the ohms to neutral per kilometer, that's going to be 10.2. So just make sure you are looking at the right row. Otherwise, you're going to get all messed up on the exam. All right, and what I'm going to do again, I'm just going to highlight here the ohms to neutral per 1,000 feet. So when I look at this table in the future, it's going to remind me of which row I need to look at if I am doing this on a per foot basis. And remember, it's 1,000 feet that they're giving us the ohms to neutral for. So the answer that we got in our question was 1 AWG. And again, we are looking at alternating current resistance for uncoated copper wires. So, and again, we're looking at what type of conduit, and that was EMT. And in this case, that EMT is going to be steel. But be careful because the EMT might be made of some other metal. So you just have to make sure that you're looking at the right type of material for that conduit. All right, so let's continue. Let's find 1 AWG AWG. And let me shrink that down a little bit so we can see all of this here. All right, so here I found 1 AWG in the first column. And if I look down here, I can see 0.16. And that's where I got that number from. And again, that's 0.16 ohms to neutral for 1,000 feet. We've already finished step 2, so let's go into step number 3. Now we're going to use Ohm's law to solve for the exact voltage drop. And E is equal to I times R, where E is equal to voltage drop. I is going to equal the amps, which we also call the current, and R is going to equal the resistance in ohms from Chapter 9, Table 9, AC, resistance and reactance. All right, so let's go plug in these numbers now and see what we get. So E is equal to 30 amps times 0.16 ohms times 600 feet divided by 1,000 feet. And you may be asking yourself, hey, Steve, where'd you get the 600 feet from? In the question it said 300 feet. Well, when you're using Ohm's law, you got to take the round trip distance, and you have to multiply it by 2 for single phase. All right, so don't make that mistake on an exam, because remember, I'll kind of draw it here a little bit. So, let's say, we've got our ungrounded conductor, going over here, and then I'm going to make another color here. I'm just going to make that a red so that you can see the difference. Okay, and that's actually a bad choice. But if I do it in white, you're not going to see it. But you know what? You're just going to have to make believe that this is a white or gray conductor. All right. So then we've got this other conductor coming back. And imagine that is the grounded conductor. So what happens is that we've got 300 feet going this way. And then we've got 300 feet going back home, and that's going to give us 600 feet, and that's where we got the 600 feet from. Now you might be thinking, I just looked at that voltage drop formula. Let's look at that again. Let's see why we had certain numbers in there. So if we look here, we could see that in our voltage drop formula, we had the number 2 in here for single phase. And that's there because of the same thing that we just showed you in Ohm's law. That single phase, you're going to use the number 2 in the voltage drop formula. But when you're using Ohm's law, you're going to have to multiply that distance one way by 2 to account for the round trip. All right, so let's go back here and let's continue solving this problem. So now we've got E is equal to 30 amps times 0.16 ohms times 0.60. And, don't forget, we got that 0.16 ohms, from the table in Chapter 9, Table 9. And again, that was for 1,000 feet. But because this distance is 600 feet, we're going to take that 600 feet divided by 1,000, and that's going to give us 0.60, which is the same thing as 60%. So now we've got E is equal to 30 amps, which is equal to 0.096 ohms. And now E, for the voltage drop in this case, is going to equal 2.88 volts, and that's equal to the exact voltage drop. So I wrote down here the exact voltage drop percentage is 2.4%, and that's 2.88 volts divided by 120 volts, and that gave us 2.4%. And if you remember in the voltage drop formula, we needed the exact circular mils of 77,400 so that we would limit the voltage drop to no more than 2.5%. But because we used that next size up and that was in Chapter 9, Table 8. And for 1 AWG, that was 83,690 circular mils. And because we used a larger conductor, that was other than necessary, our voltage drop actually decreased down to 2.4%. All right, hope you enjoyed this question. And again, make sure that you become familiar with Chapter 9, Table 9, and then also become familiar with our other table that we spoke about, and that is Chapter 9, Table 8 in your NEC codebook. All right, see you on the next question.